Alright, so this is NCCER Instrumentation 4 Module 4 Digital Logic Circuits. I'm going to start with Section 2, and at the end of this video I will go back and go through Section 1. So, if you're just tuning in for this video, we're going to start on Section 2 and then go back and hit Section 1 whenever we have completed. So, not that. Section 2, digital memory circuits. Going through some of the trade terms. You need to know what bit means. We've talked about in the past about words, and it also has the trade term word is the last one in this. A word is a group of bits, but a bit is just part of a word. So a lot of times your words are made up of 4 bits or 8 bits, stuff like that. And that's just ones and zeros strung together in order to create larger things. We'll talk about a flip-flop quite a bit, edge triggered versus level triggered. We're going to talk about, but no exact highlights in any of the trade terms. For 210, basic memory elements. The first 2 sentences are highlighted in 210. The simplest memory device stores just a single logical value, the logic 0 or 1. This is known as a bit, which is a contraction of the words binary digit. Bit is a binary digit. The RS flip-flop. This is going to be I think the beginning of this first paragraph. This is going to be your simplest flip-flop. For the function of these, like if you're reading through these, you need to know what the output is. So just going through the flip-flop, this box, the S is going to be for set, stores a logic 1 in the flip-flop. The R is going to be for your reset. The Q represents your output. So this is your normal output. And then anytime you see like a letter with a line over it, that means not. So I think it said that somewhere in Section 1. Like if you put a line over something, that means not. So this is the normal output. This is the inverted output. Those will always be opposite, whatever they are. So this RS flip-flop just stores a digital value of 0 or 1. So if I put a 1 in my set, my Q will turn to 1, my Q naught will turn to 0, and then this will hold the output at 1. The highlight that I have is in the last paragraph on page 11. The 4th sentence through the end of the paragraph on page 12 is highlighted. A challenge in analyzing the RS flip-flop lies in the fact that the outputs of the circuit are connected back to the inputs. Thus, any signal that is input to the circuit goes through the circuit and returns to the input lines. As a result, the input signal has multiple effects. This method of connecting a circuit output back to its own input, is called feedback. A feedback connection is essential for giving a logic circuit memory capability. So, this is where you would make up, just walking through, let's walk through this NOR RS flip-flop, right? So remember, this is the symbol for what? NOR, because it's an OR with a bubble. The bubble gives it the not. So remember, a NOR will act directly opposite of an OR function. So if I have either my R or my Q naught coming back into here, if I have either one of those, this is going to output a 0. Same thing for down here. If I have my set, if I don't have my set, it's going to output this. So walking through my first line, if I don't have set, I don't have reset, nothing is going to change on my output or my output now. Okay? Next line. I put my R at 1. So I put a 1 into here. Right? So if I have 1 in an OR function, this will be 1, but it'll change this to a 0, which is going to change my Q to 0. My Q naught is always opposite of what this is, so it's going to change it to 1. My Q naught changes to 1, and it's going to reset. Same thing. My reset turns off. I put my set on. Turn set into this. My reset's 0. What?
Room? Next door.
I've never heard that noise.
Okay.
Is that the camera? Alright, don't know what that was. Kind of lost track of where I am. The biggest thing with this is if you push both of these at the same time, these are just gonna jump back and forth between 1s and 0s, and that's called illegal mode. Like you can't hit. It's like hitting on and off and holding them both down at the same time, right? It's not illegal, but it's not gonna work. That's the main thing I want y'all to get out of it. I have a ton of highlights on page 12. The whole second full paragraph is highlighted. The logic 1 output from Q is connected back to one of its inputs on the lower gate. The lower gate now has the logic 1 inputs. The original input signal has been traced through the entire circuit in a figure 8 pattern. Since the lower NOR gate needs just a single logic 1 input to maintain its output logic 0 state, the logic 1 at S can change to 0 and the output will not change. In other words, the circuit is acting as memory. Sounds like a lot, but pretty much it's just saying when you hit set, it's going to hold a 1 at the output. Next paragraph is a separate highlight. Now examine what happens if the R input changes to a logic 1 while the S input stays at logic 0. Do the same analysis procedure, tracing the signal around the circuit in a figure 8 pattern. If you do this analysis correctly, you'll discover the circuit now outputs a logic 0 on the Q and the Q1 and a logic 1 on the Q naught. In other words, the flip-flop is reset, storing a logic of 0. This is illustrated in figure 18C. Next paragraph, the first 2 sentences are highlighted. In summary, the NOR-based RS flip-flop has the property that whenever the S input is changed to a logic 1, the circuit will become set and the Q output will be logic 1. Whenever the R input is changed to a logic 1, the circuit will become reset and the Q output will be logic 0. I know this sounds this a lot. It just sounds like a bunch of words and stuff like that. But the only way, like I can't just sit here and talk at you for you to understand this. The only way to like fully get this is to like sit down and follow this stuff through as you're reading through it. If you really want to get to know how this stuff works, I can only talk so much. They only have so many words for this. Like walking yourself through these is the way to kind of learn these. But if I'm being like, I want you to kind of know how these work for the principles of troubleshooting. But for our purposes of like maintenance and stuff like that, not insanely important. I wish they just did the and or not and functions and stuff like that, but they build on these. And you'll see why at the end of this section it'll talk about why this stuff is super useful, but and why they use them. But for our purposes, I'm not dead set on you guys knowing how to do all of this. Okay? Excuse me. Last paragraph before 212. Everything except the last sentence is highlighted. What happens if you try to activate both S and R at the same time? Make them both logic 1. If this happens, the RS flip-flop behaves illogically by outputting logic 0 on both Q and Q naught. This condition is called the illegal mode and shouldn't be used. It's the last paragraph before 212, everything except the last sentence. Page 13, 220, clocked logic. Alright. Clocked logic. So they can build, like I talk about, they can build and build and build. They build these to where, like this is how like a digital watch works. Okay? Like it's how it keeps time and stuff like that. Inputting and outputting ones and zeros. And they just combine all of these different pieces of logic together in order to get stuff to set. So like you have like a whole set of stuff for like the second hand, so it'll count all the way up to 60. Once it gets to 60, it'll set something in the ones column, so you have like 1 minute, and so on and so forth. And they just keep building the stuff larger and larger. Clock signals 221 on page 13, right hand side of page 13. That first sentence of that first full paragraph at the top right of 13 is highlighted. Digital circuits that must be synchronized or connected to the clock generator so they can monitor the clock signal. The last sentence of that paragraph is an online test question. For example, some circuits are edge triggered. This means they will only act if the clock signal is changing from a logic 0 to a logic 1 rising, or logic 1 to a logic 0 which is falling. So they're only going to change when something is changing state. The next paragraph, first two sentences, are a separate highlight. On the other hand, some circuits are level triggered. They act when the clock signal is at a particular logic level, logic 0 or logic 1. Two. So you can kind of see up here on the board, or it's on the next page, but this would be edge triggered. So it's when it switches, then level triggered is whenever it's on the different levels. Timing diagrams, 222. The whole first paragraph and first sentence of the second paragraph are my highlight. Truth tables work very well for describing the behavior of many digital circuits. However, they don't work well for clock logic since they cannot indicate the circuit's behavior over a period of time. For this reason, engineers and technicians use another tool, the timing diagram, to show the behavior of a clocked circuit. A timing diagram is a kind of graph with time as the x-axis or the horizontal plane. So that is your clock logic is this right here. This goes between 0 and 1. Moving on to page 14 and 15. 224, the D flip-flop. First two sentences of 224 are highlighted. Two versions of the data, or the D flip-flop, are shown in figure 25. Examine the inputs and outputs. The D input is used to both set and reset the flip-flop, instead of a pair of inputs as the RS flip-flop. Moving on to page 16. Like I said, I'm going to go somewhat quickly through the end of this chapter and stuff like that. Like, it sounds horrible, but I want you to pass this test. I don't want you to harp on this stuff too much, okay? Because I had to learn this stuff in college and stuff like that. Did you? I'd rather you know, like, this is what I want y'all to get. Like, relating that stuff to this in a simple way is what I want y'all to get from this chapter. The JK flip-flop 225, second paragraph that's on the right-hand side of 16, first sentence is highlighted. The JK flip-flop differs from the clocked RS in that instead of having an illegal mode when you activate both J and K at the same time, the JK flip-flop does something special. It toggles. JK flip-flops are used quite a bit. 230, larger memory devices. I've got the everything on page 16 going into page 17 highlighted. Not the whole paragraph, but just the sentence that continues on to 17. Flip-flops are useful as memory devices, but they are somewhat limited since they only store one bit of information. In many digital systems, it's more useful to store groups of bits organized into words. A word can be any size, although most sizes are multiples of 4 bits. Probably the most familiar word size is the byte, which is a group of 8 bits. Last two sentences of that paragraph are highlighted. A register is a memory device that stores a single word. It is made up of individual flip-flops connected to a word, connected to work together. So if you look at the bottom of the page, you can see figure 30. So this would be like a memory device. So do y'all remember how binary works? So if I had a 4-bit binary word and I wrote 0, 1, y'all remember what the places are? Remember in binary you go from right to left. So the first would be, this would be the 1 section, 2, and then they keep doubling, 4 and 8. So if I had 0, 1, 0, 1, this would be 1 plus 4. So this word would give me 5. Does that make sense? Like this column is my 1s column, this column is my 2s, this column is my 4s, this column is my 8. So if I have 1, 1, and 1, 4, I have 5. Does that make sense? Mm-hmm. So that's how they're making this stuff work. Like they're combining this stuff together, and these are my outputs in my 4-bit register made of D flip-flops. It's a lot, but I'm trying to relate it as easy as I can. I gave you all the highlight in 2, 3, 1. Basic register. First, this is what I just said. First two sentences in 2, 3, 1 is highlighted. The simplest kind of register is shown in figure 30. In this example, the register holds a single 4-bit word. It's made up of 4 D flip-flops. I'm going to continue on. I'll just say section 2 review. I'll give that to y'all with the homework along with the other stuff. I'm going to keep going into section 3. All right. Counter circuits. 300. Alright, on page 19, it's going to talk about binary numbers. This is going to talk about the different number systems. I have the first 2 paragraphs highlighted. You're going to have 2 questions come out of the first 2 paragraphs. I'm just going to read through them and talk about them. The binary, this is in 311, the first 2 paragraphs. The binary number system has rules that are similar but somewhat similar than those of the decimal system. Binary starts by representing a quantity of 0 with a 0 and a quantity of 1 with a 1. However, no binary symbol exists for a quantity of 2. This problem is handled the same manner as it's handled with the decimal system. No individual system in the decimal system represents a quantity of 10, so when you reach the maximum number digit value, which is 9, you add another digit to the left and set it to 1. Then you reset the original digit back to 0. This results in a 2-digit number, 10. In binary, 2 is represented by resetting the original digit to 0 and putting 1 to the left. Thus, the 2 is represented by 1 0 in binary. This process can continue indefinitely. The second column of the table 14 shows the binary equivalents of the decimal numbers 0 through 15. So if I have binary versus decimal versus binary, so same thing. I've got 0 is 0, 4-bit binary, which is what I was talking about over there. 0, 0, 0, 0, still going to represent 0. 1 is the same as 1. 4-bit binary would be 0, 0, 1. All right? All the way up to 15. So if I have in 4-bit binary, if I made this 1, 1, 1, 1, I would have 1 plus 2 plus 4 plus 8, which would be 15. Does that make sense? We're just going to talk about how to get between the two. Like, you kind of need to. You should know how to get from 4-bit binary into decimal. Flipping the page. It's a long section. Hexadecimal numbers. 312. So, binary is base what? How many numbers can you have in binary? 2. Decimal is base what? Our normal numbers. 10. Everything's in base 10. Like count to 0 through 9 is 10 numbers. So we have 10 numbers. Hexadecimal would be called base 16. So they have 16 different numbers or letters that they can use to represent different things. My highlight in hexadecimal numbers is in that first paragraph in 312. Right after where you see decimal and binary in parentheses, about halfway through, the rest of the paragraph is highlighted. So these digits are the familiar 0 through 9, along with the letters A, B, C, D, E, and F. The digits 0 through 9 work just as they do in decimal. The letter A stands for the number 10, B for 11, C for 12, and so on. This means that each digit position can represent a value 0 through 15. So, decimal, binary, 4-bit binary, hexadecimal. 0 through 9 is going to stay the same as decimal. Okay? The only difference with hexadecimal, once we get to a 2-digit number, they switch to letters through F. So you just need to remember, once you get to 2 digits, A through F is 10 through 15. Okay? That's the main thing I want y'all to remember. Counter circuits, 320. 321 binary counters. This short section has 4 different highlights. First 2 sentences are my first highlight. Figure 31 shows the schematic for a simple binary counter that counts from 0000 or 0 decimal to 15 decimal. It's made up of 4 JK flip-flops with their J and K inputs both activated. Next sentence is a separate highlight. As previously discussed, a JK flip-flop configured in this way toggles back and forth between 0 and 1 every time it sees an appropriate clock edge. So it's edge triggered. Top right of page 20. Notice that the Q output from the flip-flop feeds into the clock input of the next stage. So all that's saying is notice that you have 4 outputs. Your output also feeds into the clock of the next stage. All that's saying. And then the last 2 sentences of that paragraph are also highlighted. Note that the binary count at the bottom of the timing diagram, the counter begins at 0000, counts up to 1111, and then rolls back to 0000 before the count starts over. Other counters, 330. Moving on to binary coded decimals. I'm going to give you the highlight, and I'll talk about it. Second sentence of 331 is the highlight, the one that has the BCD number blue highlighted. A BCD number is a binary number that ranges from 0000 to 1001, or 0 to 9 in decimal. They don't talk about. All right, just so you know how BCD works. This isn't in the no, I'm not going to talk about it. This is going to be more confusing. 332 up-down counters. I've got the last 3 sentences on the page highlighted. These include an input labeled direction that controls the count direction. For example, if the input's connected to the logic 0 value, the circuit counts up. If the input's change to a logic 1, the circuit counts down. Alright, continuing on to section 4. Just got pretty much 3 pages left, but I've still got several highlights. Okay? So section 4. Arithmetic circuits. So these calculators like this are full of digital logic. So literally all this is doing is every time you push a button on here, this is setting something like this. You're setting some type of code in there that's going to create something else. Like, it's crazy how much like computing power, like how much digital logic is in this simple calculator stuff. But this is how calculators work. 410 arithmetic circuits. The first 2 sentences are highlighted. The arithmetic circuits in a typical computer are extremely complicated. However, all arithmetic fundamentally comes down to is just one operation: addition. 411 principles of addition. The first 3 sentences are highlighted. Decimal addition is performed 1 column at a time. If the sum of the column is greater than 9, if it is a 2-digit number, it generates a carry into the next column. When you add the numbers in that column, you include the carry from the previous column. It's like going back to elementary school. If it goes over 10, you have to add on to the next column. Section 412. A simple adder. This paragraph has an online test question in it. I'm going to read through the paragraph and then I'm going to tell you what to key in on. A binary adding circuit is a combination logic circuit that has 3 inputs and 2 outputs. Figure 33 shows a schematic symbol for a binary adder that can add 2 bits. The A and B inputs accept 2 bits to be added together. Cin accepts the carry from the previous column's addition. The S output is the sum. C output is the carry to the next column. You want to key in that it has 2 outputs. And the 2 outputs, if you look up here on the board, the outputs are the S, which is the sum, and the C out, which is the carry to another adder. Those are the 2 outputs of a simple adder function. Next paragraph, first sentence is highlighted to go along with it. Or not, excuse me, doesn't go along with that highlight, but goes along with that section. Because adding just 2 bits isn't very useful, the circuit is replicated many times until there are enough bits to perform useful additions. Inside the box, 413. I've got the 3rd and 4th sentence highlighted as my first highlight in this paragraph. This is talking about figure 35. which is this one, I believe. This circuit is actually two separate circuits. The first one, made up of two XOR gates, adds the three input bits A, B, and C in together and generates the sum. The next sentence is a separate highlight. The second circuit is made up of three AND gates and one OR gate. Works out whether there needs to be a carry to the next stage. 420, decoders. The whole thing is highlighted. Moving into page 23. Digital circuits work with binary numbers internally. However, it's often necessary for digital information to be presented in a more user-friendly way. Video displays and LCD panels offer a very sophisticated way to make information available to operators, but in many cases these devices would be overkill or simply too excessive for the application. Some displays, such as a status light or number-only readouts, are often sufficient. Special circuits are required to convert binary information into other forms, such as decimal numbers or patterns of status lights. Key in the last sentence of this is the most important. Circuits known as decoders perform this function, converting digital information from one form into another. Still on page 23. I'm not sure where the I do have, you're going to have a question in the section review come out of table 15 for this simple binary add or truth table. You just need to know that you're going to have a question come up. The section review is going to have a question come out of table 15. Basic decoders 421 going on to page 24. This second sentence on page 24 is highlighted. The circuit examines the number coming from the inputs and activates a unique pattern on the outputs. So, this would be a decoder, right? Or not right, this is a decoder. So it has all of this digital logic. Anybody remember what these are called?
Inverters.
Inverters or what function?
And? Nor? No, nor. The and.
It starts with an N. These are not. So not and inverters are the same. So these are inverters. All these are what? Ands. So digital logic circuits converted over to inside a box. So it technically just has three inputs. So input, 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 and then you can get 8 outputs. 8 outputs because you have Q0. Okay? Where this is useful is something that has 8 outputs. You've seen those before? Like scoreboard signs. So like the letters that work like this, all of these different ones, those are the outputs. So this is like my outputs A through G, A, B, C, D, E, F, G. So all the like scoreboards and people pushing buttons for scoreboards and stuff like that, that is all digital logic. But breaking it down, breaking it down, I'm just trying to see which combination of lights I'm turning on, and there is a wad of digital logic that goes behind that. Where something seems super simple, it's not. Does that make sense though? Like where they actually use this? I don't care about y'all being able to like work your way through the digital logics and stuff like that, but seeing where it is useful is what I want y'all to know, and related to ladder logic. Complex decoder 422. First sentence is what you want to. First 2 sentences is what you want to key in on. Sometimes a more sophisticated decoder is needed. Many machines have numeric displays that use 7-segment LEDs. That's where I got into this. That is a 7-segment LCD. Right? 4, 5, 6, 7. 7-segment LCD. The rest of the paragraph is also highlighted. These are made up of 7 bar-shaped LEDs arranged in the shape of the number 8. By lighting up specific segments, the numbers 0 through 9 can be formed on the display. Controlling one of these displays requires the decoder to take a binary number between quadruple 0 and 1001, or 0 through 9 decimal, and translate it to the appropriate segment pattern for that number. I don't know why, but that is usually a highly missed question on the test, talking about using a decoder to make a 7-segment LCD. Like usually, I think they ask like how many segments in LCD or something like that. 7. All right.